Hello, my name is Gaganjit Singh, and this is my project Reinforcement Learning for Unit Artificial and Computational Intelligence. Firstly, what is reinforcement learning? Reinforcement learning is a type of machine learning where we have an agent and an environment, and the agent wants to maximize a reward in that environment. So what happens is that an agent performs an action from all the possible actions, and according to the action, the agent gets a reward, and the reward, uh, according to the reward, we can calculate if that was a good reward, good action, or a bad action. Here we need to go through a few terms. Firstly, what is a state and what is a reward? I'll try to demonstrate these topics through examples. Think of a light switch. A light switch can be off or it can be on. So these are the two states of a light. So a light can be either on or off. If you make it a bit more complex, think of a chessboard. Every single possible combination of pieces placed on the chessboard is a state and a reward. A reward is what you get if you perform an action on the state. For example, if the light was off, you turned it on, you got, now the room is brighter, and so that can be seen as a reward. But obviously in computers this will be in numbers. In chess, if you make a move and you checkmate your opponent, that's a good move, so your reward should be higher in terms of, if you want a program like chess in using machine learning. Mostly this project revolves around q-learning, and what q-learning is that the actions that are taken are taken uh, according to the q value of that action, and every single action, state action pair, will have a q value associated with that pair. So we need, during training, we calculate these values using a formula. That formula will be, I'll mention that formula later in slides. And what happens is, when we are running anything, we would like to take the maximum value from all the possible actions that can be performed, and we make that move. That's the basic of q-learning. Other than that, q-learning, yeah, for training in q-learning, we will do, firstly we'll reset the environment, then according to the state of the environment, we'll make a random action or action according to q table. The random action is important because we want to explore that environment, and that will be useful. uh, so we would have the correct, or we can find the efficient solution of the problem. So according to that reward, then after performing the action, we'll have a reward, and according to that reward, the new q value will be calculated, and that new value will be assigned in the state action pair in the q table. Here's the formula to calculate the new q value. So how this formula works is that uh, it takes some portion of the current value and some portion of the value which is a reward, plus the maximum q value of all states and next action. So here we have few hyperparameters and a discount factor. Sorry, few hyperparameters which are learning rate and discount factor. So also another a third one which will I talk about later. Firstly, what are these hyperparameters? Learning rate. Learning rate is the alpha, and this can be visualized if we separate the equation into two sections. This section is the current value, and this section is the learned value. And the higher the value of alpha, the more importance we will give to the learned value rather than the uh, current value. So the alpha can range from 0 to 1, and it splits the value into two portions, which add up to 100%. And that's how the new value is calculated. And discount factor. This is gamma. This is a part of learnt value, and in the learnt value, gamma is calculated the max of all states and next action. So after this, the purpose of purpose of gamma is that the higher the gamma is, the more long-term benefit, long-term we're gonna think about it, long-term benefit, like long-term reward. So even if the next reward puts in a worse position than we are right now, but later, because we made that move, we'll be in a better position. uh, uh, so that's which this attribute is controlled through gamma. For example, in chess, some moves, some sacrificial move can give you better position on board. This is a way to think about it. Other than the exploration rate, it is the rate at which the agent explores. So we don't always want to make the move according to the Q value in training. That is, sometimes here and then we want to make a random move so that we can explore. This is helpful because even if we find a solution, it doesn't mean it's necessarily the best solution. So if the exploration rate is high, so we can find the better solution or the best solution, and do not stuck in local minima. If you are like in artificial neural networks, we can get stuck in local minima. We don't want that to happen here as well. I have three environments that I will solve according using Q-learning. The first of them will be a taxi problem. Firstly, I'm going to explain what is the taxi problem. So here an agent is the taxi, and it can make 6 actions. It can move in one of 4 directions. It can pick up the passenger, and it can drop off the passenger. Whenever the passenger is picked and dropped off, we get a reward of 10. Otherwise, we get a reward of, for every single step, we get a reward of -1. This is because we want to do it in least possible number of steps. So the more steps you get, the lower the reward will be. And if we drop off on the wrong place or pick up from the wrong place, however, we will lose 10 points. This is a penalty. This is a big negative reward. So our program will learn to avoid it real fast. Sorry. Now I'm going to show code and graph for the taxi problem that I mentioned. Here it is. I've already trained the Q-learning model. What happens? This is environment setting. This is if we want to take a random step. This is how many steps it takes to complete a episode. I ran it 10 times, so you can see, and then I graphed it that this is the amount of steps it takes according to, if we just take random awards. I'm gonna run it again and show you. This doesn't take that much, doesn't take that long. So this is a demonstration for that, visualizing that random steps, we don't go anywhere, it's just random steps. Only a long period of time, we luckily get the right solution. I'm gonna stop this, and here is, if we graph it 10 times, it takes thousands of steps, which is not very optimal. And nextly, using Q-learning model, this is here. I've already trained it, so I'm gonna run it for a few episodes. You can see it's picking up passenger and dropping off. It's a bit fast right now. I can slow it down to make it more clear what's happening. Like the right actions are taken uh, after Q-learning is done. So going through code a bit. So how the code is structured is that here, oh sorry, not this one. In Q-learning, the code is structured like epsilon, the amount that we want to explore, the amount of times, which is set to 0.1. So 10% of the time will be just taking random actions. The other time will take an action according to the maximum of the state. And then the updating of value. This is nothing but simply the formula that I showed you. This is a graph after Q-learning. Oops. Sorry about that. Oh, sorry, we stopped it midway. That's why the whole data didn't come. I'm gonna let it run for a minute. Oh, it's too slow. So now I'm going to graph this, and you can see the maximum is like 18 steps, 16 steps. The whole episode ends in like 6 steps and like that. Back to my presentation. Now I will in the next situation, the next environment I'll be dealing with is card pull problem. There's a major difference between this and the previous one that I'll go through. Firstly, the goal is to keep the pole perpendicular to the card. That's our goal in this environment. And the major difference is that we have a continuous observation values. Previously, every state, the environment just gave us a number of what state we are in. This time, that's not the case. This time, we'll have to calculate ourselves what the state is. So that is done using discrete k-bins discretizer. This is a function that I used from sklearn library, and what it does, it turns discrete values into turns continuous value into discrete values. And other than that, I'm also using decaying learning and exploration rate, which means that in the beginning the whole environment will be explored, and in the ending of in the last episodes, as the episode number increases, we explore less and just focus on what we learn. Explore, that's also known as explore and exploit. Now card poll, I have already trained this again. I have saved the Q tables. I'm going to submit it with my submission. Everything is same, only we are using exploration rate and learning rate, which are decaying. So this is how it looks. This is a graph of every 100 step, what's the maximum, what's the minimum, and what's the average number of steps it survived. So the episode runs for 200 steps. If we survived for 200 time steps, we will call that a victory and we will count as a win. And this is not very good, but it's still okay, because I have only, in this model, I've only considered the pole angle and pole angular velocity of the pole. So usually what happens is that the pole just slides to one of the side and hits the edge, and that's when the episode get terminated. I'm gonna show some uh, episodes of how it is like this. It's getting very stable, but this that one just hits the edge and it gets terminated. That's the default. What do you say? That's not the optimal way of doing it, but it's close enough. I am getting on average 179 steps. The next I want to talk about is mountain climber or mountain car problem. So here we want this car to be at this flag, but we can't simply just climb up this hill uh, because we don't have enough power in the car. So we'll need to build up momentum moving the car back and forth and reach the highest point like that. So we can have three steps. Firstly, with the acceleration right, the acceleration left, and don't do anything. These three steps are the actions, possible actions in this case. In the previous one, the possible actions were moving left or moving right to balance the pole. I'm going to go through the mountain car Q-learning model. It's very similar to it's almost same to the cart pole model, only few values are changed. I have mentioned all the hyperparameter values in my report, and I'm gonna demonstrate 5 episodes. So all 5 episodes were completed, and in this during training I got 100% of success rate, and every single time it just completes the environment. So we made a good model. The Q values are good. I will be providing these values with the submission. So overall, there's few ways to use Q-learning models on different problems. We can have a few type of states. We can use different types of hyperparameters, either constant or decaying. Also, we'll have to tweak our model according to what the environment requires, because in cardboard problem surviving 200 steps is a good thing, but not in case of mountain climber, because if that doesn't mean that we have reached the top. So there's a difference in that. So we have to adjust few things. Also goals can be different, so according to that we'll have to again change. Also action space depends on the computational load on the system also, and the number of states also has an effect on how long it's going to take to train or how long it's going to take to finish. So in the end, overall, it was a really good project. I really enjoyed it. I learned a lot of new things regarding Q-learning, and I also learned a bit about temporal difference. I have mentioned some few topics like that in my report. Other than that, it was really good. Few limitations with my project is the one in the cart pole. It's not doing 200 steps every time. because of I'm not taking in consideration the position of the cart. Other than that, I'm really happy with it. Thank you.